In this experiment, students would measure the temperature changes of air and water entering and leaving the cooling tower, in order to access the effect of heat rejection load and air flow rate on the wet bulb approach. Consider the surface of a warm water droplet or film in contact with an air stream. If the water is hotter than the air, it will be cooled by conduction and convection, which will depend on the temperature difference, the contact surface area and air velocity, and by evaporation. Cooling by evaporation is by far the most important effect. Evaporative cooling takes place as molecules of water diffuse from the surface into the surrounding air, and the energy required for evaporation is taken from the remaining liquid. The rate of evaporation from a wet surface into the surrounding air is determined by the difference between the saturation vapor pressure at the liquid surface and the vapor pressure in the surrounding air. If unsaturated air is constantly circulated, the wet surface will reach an equilibrium temperature at which the cooling effect due to evaporation is equal to the heat transfer to the liquid by conduction and convection from the air. The equilibrium temperature reached by the surface under adiabatic conditions is the wet bulb temperature. In a cooling tower of infinite size and with an adequate airflow rate, the water leaving will be at the wet bulb temperature of the incoming air. For this reason, the difference between the temperature of the water leaving a cooling tower and the wet bulb temperature of the air entering the tower is an indication of the effectiveness of the cooling tower. The Hilton bench-top cooling tower rig is used for this experiment, which is designed to provide an appreciation of the construction, design, and operational characteristics of an evaporative cooling system. The unit is a good example of an open system through which two streams of fluid flow and in which there is a heat and mass transfer from one stream to the other. The cooling tower rig is completely self-contained, and includes packed column, forced draft centrifugal fan, circulating pump, water distributor, water droplet arrestor and makeup tank. Let's study the concerned terms of cooling tower. Cooling range. It is the difference between the water temperature at entry to and exit from the tower. Heat rejection load. It is the rate at which heat is removed from the water. Approach to wet bulb. It is the difference between the temperature of the water leaving the tower and the wet bulb temperature of the air entering the tower. Makeup water. It is the quantity of fresh water which must be supplied to the cooling water circuit to make good the losses due to evaporation, drift, and drain down. The dry air mass flow rate. It can be evaluated through the relationship between specific volume and moisture content of air leaving the tower, and the value of orifice differential. In Stage 1, students should familiarize with the installation of cooling tower rig. Identify the various components of cooling tower rig for the measurement of air temperature, air flow rate, water flow rate and air pressure drop. And find out how the heat rejection load is simulated in this cooling tower rig. This figure illustrates the air flow path from fan air inlet to leaving the tower. This illustrates the water flow path from water tank to tower. There are thermometers for measuring air temperature and water temperature entering and leaving the tower. The values are shown in monitor. Also, there are ports for measuring orifice differential pressure and pressure drop across packing, by connecting tubes to the manometer. We have switches for main power and water heaters. And water flow meter and adjuster are on the right-hand side. The air flow rate can be controlled by adjusting the damper position as shown. Stage 2.1. We are now using packed column B to operate the cooling tower. Switch on the main power and set water flow rate at 40 gram per second. Set electrical heater input at 0 kilowatt. And fully open the damper. Record the orifice differential pressure and pressure drop across packing from manometer. Stage 2.2. Fill up water at makeup tank to the marked level and start counting the time. Check and record the water losses at makeup tank after 10 minutes. Record the air temperatures and water temperatures. Stage 2.3. Keep the water and air flow rates in constant. Increase the electrical heater input to 0.5 kilowatt, 1.0 kilowatt and 1.5 kilowatt in steps. Repeat stage 2.1 and 2.2 after each step of increased load. Stage 3.1. Change the air flow rate to about 1/2 of that used in stage 2 by adjusting the fan intake damper, keeping the water flow rate same as before. How to adjust the air flow rate? As mentioned in previous slide, we use this equation to evaluate the dry air mass flow rate. Let's take an example with these values. We get the air mass flow rate at 0.552 kg per second. And 1/2 of the air flow rate to be used in stage 3 will be 0.276 kg per second. Now, using the same equation, we can calculate the orifice differential pressure when the air flow rate is halved. Then adjust the damper position until the orifice differential pressure reaches the target level at manometer. Stage 3.2. Keep this damper position and keep the water flow rate constant at 40 gram per second. Adjust the electrical heater input to 0 kilowatt, 0.5 kilowatt, 1.0 kilowatt and 1.5 kilowatt in steps. Repeat 2.1 to 2.3 under this reduced air flow rate and record the readings. When the experiment is completed, please switch off all electrical heater powers, fully open the air inlet damper, turn the water flow rate to 0 and let the fan to dry the packed column. In the logbook report, please complete the result sheet by calculating the air flow rate, heat rejection load, wet bulb approach and amount of water loss due to evaporation. Plot graphs to illustrate the relationship between heat rejection load and wet bulb approach for each of the two air flow rates, and briefly describe the relationship. Also, please try to do the supplementary. Enjoy the experiment. Thank you.